Hello everybody, my name is Tan Bui. Today I would like to present our paper of value embedding approach for access control, and hopefully through this paper we will be able to find a new way to construct a more efficient access control model. Before we go any further, we're gonna have an overview of our presentation today. First of all, we're gonna discuss all the related work currently working on the access control. Then we're gonna show our contribution with our proposed methodology, and then we're gonna move on to the results and the finding that we having after we conduct our experiment. Finally, we're gonna discuss some limitation and the future work for our method. So, first of all, we all know access control is one of the classic problems of cybersecurity, as it's considered to be the front line to protect every system before from any intruder. However, it is an essential issue, so it has been studied continuously since over 40 years. While the topic has been explored in that long period of time, there are still many drawbacks that hinder researchers from reaching an optimal solution, such as the high reliance on human intervention. So it may cause either excessive or lack of resources distribution toward correct user, especially in a larger organization, and policies sometimes become very wonky due to the size of the organization that make the system administrator have spent a lot of time to solve the complicated problem. While there has been many access control research going on, we are classify them into two main categories. Our first category is classical policy mining approach, where they will have the three main methods to generate the policy mining. Those are the rules-based access control, attribute-based access control, relationship-based access control. There's also hybrid variation by taking aspect of one method to apply into another method, such as taking a certain rules from the rule base and combine with attribute base to create a new access control method. And those we also consider the hybrid method. A newer method to building access control model is to use machine learning for policy mining. This is considered a newer and very promising because it's the nature of machine learning to be able to work with massive amount of data and derive quicker results. For this approach, researchers usually develop algorithms to help extracting certain aspects from user requests before feeding them into a classifier. The classifier will decide whether those aspects satisfy for access to grant an access or deny the access. And this one have a lot of potential because it's work faster and also reduce the amount of human intervention, which allows machine to be able to have more control over the decision, and will reduce the amount of system administration attention to help with the system. In our work, we would like to propose a machine learning approach toward access control problem. Unlike previous work, our model is attempt to capture the contextual information of each token so that the model can make appropriate decision. So to achieve the goal, we should create an embedding layer from historical data of access by various users to convert each attribute value into an empirical vector with a set dimension value. A machine learning model will be used to train these empirical vectors to generate appropriate decision for each access request. Here are the set of mathematical notation that we use to define our problem. We have the set for each user information and the system state. We also have the set of possible value for our user and the system state. And we define the access request as a tuple. And then from that tuple, we can assign the decision associated to each of them. The information will be extracted from the log, which we define as an L here. And we also have the parameter that we use to benchmarking our experiment to make sure that our model is performed as we expected. For experimental benchmark, we will use the standard evaluation matrix, but the key metric will vary depend on our test scenario. Since we have the balanced dataset and imbalanced dataset, we will use the three main benchmark score as accuracy, precision, and F-score. Where in the imbalanced dataset, the F-score will be more focused on compared to the other two. In this diagram, we'll show the procedure of how we train our model. All the request information will be concatenated into only two columns of the access request string and the label for whether the access being accepted or denied. And then the data will be split into the training and the testing set. We'll use the training set to the access string in the training set to train the embedding layer. And in this case, we use the word2vec with the scriptgram model because it has been known to working very well with large amount of data. Then for the label, the access label, we use the one-hot encoding to make the label value to 0 and 1. And then we'll use the embedding value with the encode label to train our model using the extreme gradient boosting model. Then we use the same embedding layer to verify with the testing data and to convert the data into embedded vector. And then we're using the same access control model to verify whether to generate our access decision. And then we compare with the original access decision from the testing dataset to benchmark how well our model working. So for the experimental data, we use the data provided by Amazon in the UCI archive. The data includes over 36,000 employees, accessibilities over their 32,000 resources. We populate the data using the cross product and matching user information to each resources and their accessibility. This method generates over 1 billion rows of data. Most of them are rejected users from accessing the resources. So we apply the sampling method by class for each decision value to generate different datasets with variation in size. And we also generate the balanced dataset and imbalanced dataset to test whether our model being stable to work with different scenarios. Each dataset is split into training and testing set with a ratio of 80% and 20%, where 80% is used for training and 20% is used for testing. Our attribute value for access request emerge into a string with space separator. Embedding layer are trained using word2vec model. We perform multiple training process and using loss value as an indicator to find the optimal value for the dimension. Extreme gradient boosting is selected as a classification model as we try with different model and we found this one to be one of the best. For access control generator, we also perform research to find the optimal parameter for our model in each scenario. So to test how efficient our model against other model in the past, we will test with the DLBAC model using the same data sets for each scenario because this model is very new. There are many parameters that need to be fine-tuning in our procedure. However, we will be only focusing on the key parameter that impact on the accuracies for our procedure. For the embedding layer, vector dimension is an important parameter. So we perform a grid search with an incremental of 50 for this parameter. Then we collect the training loss and elapsed time to plot training graphs and decide on a candidate's value for the vector size. In our experiment, the vector size of 150 seemed to be the best candidate considering both time and loss value from collected data. For the access control generator, we use XGBoost and we perform a research with various configurations. We also perform the fivefold cross-validation to ensure the model stability and using the area under the curve ROC score as a benchmark to select our best model. In our experimental, the results indicate that our proposed approach performed better than the LBAC across in our dataset and with our benchmark a parameter that we propose, showing that contextual embedding layer achieve a significant better result in capturing the underlying information. Another training, we noticed that our experimental outcome improved as the dataset size increased, which showed that our model would perform better in a larger dataset. And for the imbalance setup, it also yield better result than the balance setup, with imitate more to the real life scenario because in a real life scenario, mostly people will know what the resources they are capable of accessing to. So it will be less likely to be a reject case and showing that our proposed approach have a promising aspect to apply to a real life scenario. So, in conclusion, we found that our proposed approach yields significantly better results in different setups across our metric, showing that its capability of learning the underlying context of the access request is also have the transferability to similar instance and a significantly lower training time, which show it had a potential for lightweight application, especially in a cloud or force computing system due to their limited hardware capacity. There are many possibilities for extension in our future work, such as how our model gonna be working if an unknown token being introduced into the system, because unknown token has not previously trained in the system. So how will the model handle that? And what happens if the token represent different state? So it have the same code number, but it will be used to present different state of the system, or maybe different meaning that for the user attribute. Another thing we was thinking of is approach with by assemb assembling our model with the traditional access control to improve its accuracy and having a smooth transition from having a lot of human intervention to having to being more automated. Here's some reference for our information about the experimental data and the model that we use to compare our experimental result with. And thank you very much for your attention for the presentation. And if you have any question regarding to our procedure, our paper, and our model, please email me as tbui@uark.edu. Thank you.